Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to review temporal difference learning. Temporal difference learning is an algorithm that is unique to reinforcement learning. Whereas with Monte Carlo, we need to sample returns based on an episode, with TD learning, we estimate returns based on our current estimated value function. Specifically, we looked at what is called TD0. So instead of using G, which is the sample return, we use R plus gamma times V of S prime, which estimates the return from the next state and onward. R is still a sample that we got from playing the episode. In the previous reinforcement learning course, we made a big deal about calculating means. The most basic but naive way of calculating a sample mean is to collect all the samples in an array, sum them together, and divide by the length of the array. The major disadvantage of this is that it requires us to store all the samples in memory, which is space inefficient. Instead, we can multiply the equation for the sample mean such that the sample mean after collecting t samples can be defined in terms of the sample mean after collecting t-1 samples. This form is useful not only because it's space efficient, we only need to ever hold one value at a time, but it also looks a lot like gradient descent. And in fact, in the previous reinforcement learning course, we showed that this actually is an instance of gradient descent. So the key is that the learning rate doesn't necessarily have to equal 1 over t, it can be anything. Usually we use the symbol alpha. This brings us back to TD0. Remember that instead of sampling the return G, we'll estimate G using the current reward and the next state value. One immediately obvious advantage of this is that it allows us to use true online learning. We only have to wait until time t+1 before we can update the value for the state at time t. This is opposed to Monte Carlo, where we have to wait until the entire episode is over before we can calculate the returns and update the values. This is especially useful for episodes that are very long and non-episodic tasks. It means that we can learn during the episode rather than waiting until it's over. For the control problem, we looked at two different but very similar algorithms. The first algorithm we looked at is called SARSA. Essentially, it is policy iteration applied to TD learning. It's called SARSA because the equation makes use of the last state action pair, the reward, and the next state action pair. The main idea is that the action is always chosen based on the current value function, which we know as the policy improvement step. Let's look at some pseudocode to solidify this idea. First, we initialize Q arbitrarily and 0 for any terminal state. Next, we enter an infinite loop. Inside the loop, we start a game. We get the first state and select the first action based on epsilon greedy and the current Q. We'll call this the tuple SA. Inside this loop, we start another loop that ends when the episode is over. We do the action A to get to the next state S prime and the reward R. We then choose the next action based on epsilon greedy and the current Q. We call this A prime. Next, we do our update for Q of S and A, which depends on Q of S and A, R, and Q of S prime A prime. Lastly, we update S to be S prime, and we update A to be A prime. The final algorithm we looked at is called Q-learning. Q-learning is very similar to SARSA, but it's an off-policy algorithm, because the update equation remains the same no matter what action we take. The difference here is that the return is now estimated based on the max of Q over all possible next actions. In other words, it doesn't matter what action we take next, because we're always taking the max over all of them to update Q of SA.